Logical sciences. The first speaker is Nicolas Lopez. He will be giving a talk on multi-objective optimization of a hybrid microgrid with genetic algorithm and simulation. His main advisor is Dr. Jose Espiritu. 15 minutes for the talk, 5 minutes for questions.
Good morning, everyone. This paper, we're currently working on this project. We're planning to present the results on May next year, but so far we are presenting what we have so far. So a little bit of the introduction for the agenda and then the background of the problem, and more description of the problem, and then the formulation that we're adapting, and then the genetic algorithm that we use, and then the simulation that we involve in the genetic algorithm, how we modify the genetic algorithm, and some results that we have so far. Okay, for introduction, we know electricity is an angular stone for our society, whether we play Nintendo or watch TV or do anything, we are pretty much consuming electricity. Basically, the electricity we're using right now has been created 1 or 2 seconds ago in a power plant very long distance away. So it's a very fast process. This is the process. Definition is the creation of production in big power plants. It doesn't matter what type of power plant it is. Basically, the same process is created on a certain site, and then the transmission line is very high voltage to transmit the electricity for long distances, and then at the end, the distribution lines, which is here in the cities or where the electricity is consumed. By the way, this last portion is where the main failures occur, actually, because of the interaction with humans and other different behaviors that occur at the end. So, the electricity may be produced by renewable or non-renewable sources, as we know. The renewables, there are many types. Wind power, we have photovoltaic, solar thermoelectric, hydropower, geothermal energy, biomass, tidal energy, wave energy, landfill gas, so we have many, right? Out of those sources, we have to decide, well, this is the current state of the electric grid in the United States, but basically, most people usually believe that the electricity is one big power grid for the entire nation, but that's not the reality. In reality, we have different power grids that are interconnected within each other. Basically, we have 3 sections in the United States: the east, the central side, and then the west. Of course, each production side has its own distribution and transmission lines, and then at the end, they all interact with each other. Coal power plants in the United States, nuclear power plants over here in the United States, gas power plants, hydropower plants, oil power plants, biomass power plants, so this is renewables, solar power plant, we have actually 2 over here, difficult to see. Wind farms, we have some in the middle right here. But we see that we have a lot of capacity for solar energy, for example, here in the desert in the middle. Also, we have much capacity for wind in the center, also near the coast, but primarily in the center. So, in addition, the electric demand is growing. That is the growing. It's not the total behavior. It's the behavior of the growing, like the slope of the demand by itself. So we have the only decrease that we have is in the 2008, the crisis, where actually business closed, and then that's a single decrease in electric demand that we have. So the projections have here outdated data, but basically the same for this year. Doesn't matter what we do, if we do good economic growth or low economic growth, basically the green part, we can see that's going to at least double, or it's doubling, so it's growing very fast, so we need to address the problem of introducing renewable energy into power grids. We can see here the prices in electricity. We see that with high economic growth, the price is going to go up. It's not because the companies want actually to charge more, but with high economic growth, we have much more demand, which cannot be easily satisfied by the current companies, so the price goes up. So it's important to analyze hybrid power systems before changing from traditional to renewable energy. There is a state of hybrid power system where they both share the power grid, so we have to do that. Previously, share some other works that have been dealing with this. So basically, summarizing, what is the problem? So we have many sources of electricity, and we have to decide which combination of sources is a good combination regarding price and regarding pollution. How to make such decision? That is the question of our project. So basically, the problem is like this. We have a certain demand of electricity in a certain location, and then we have a supply. The supply may be a different curve from the demand. So when we overproduce, maybe we store the energy, and then we release it when we are overreached by the demand. The combinations that we can choose from are very differently. For example, fossil fuel generators are very stable as compared with the renewable sources because they are being on the market for more time, so it's easier to control them. Also, the wind and solar energy, they depend on meteorological factors. It's not very constant, even though they have different patterns that they're related, but not very directly related. So it's it can be complex to see that. So basically, this is what we have. We have a demand over there, and then we have a bunch of sources or supplies that we can combine in every way we want, and then at the end we finally have summation of what we have in supply, and then we compare with the demand, so we have a balance, right? Where we have overproduction or underproduction, then we can play games like with game theory or agent-based modeling for deciding where the storage is going to occur, where to release it, and many things that we can do with this. So right now, what we see is that we have many solutions depending on each combination. In this case, we have two objectives, the total net present cost and then the lower bounding potential that we can evaluate for each combination. So how to decide which is the best solution? Well, if it's single objective, let's say minimize cost, we'll pick the cheapest, right? But if it's to minimize the lower bounding potential, we'll pick the cleanest. What we do over here is we try to do the multi-objective evaluation. So summarizing, what we have is a certain set of functions. Then we have many combinations where we can pick different components, different types, different sizes, quantities. So at the end, depending on what the environment is, we have different sources, right? So it's like a game where we kind of have many choices, where we have combination 1, combination 2. Every combination can be evaluated for different objective functions. And then when we come out with a closer look at this, we have a formulation where we have two objective functions at this time. The cost can be do in a discrete manner, where the components and every part can be counted as a single unit. So from each single unit, we can go and create a cost function. The global one potential on the other side is continuous, so we have to integrate what's the behavior of the components within the hours, within the times. And then at the end, we also have a value. And then basically over here, the B is for balance. Basically, what it says is the balance has to be positive. That is, we cannot go any electric outage where we are. Also, over here, all these functions are basically depending on the type of component. It goes to a certain type of equation or another type of equation depending on what type of component you're talking about. For example, wind energy. If we're talking with wind turbines, we have this equation, which depending on the wind turbine and depending on what components we're talking, we can modify some of the values to model the wind turbine. Also, inputting the wind. This formula is common, so it's nothing special over here, but it's just so you see, it can be strange, right? Diesel generators, also different type of equations. Where we have a fuel volume, etc. So it's a different type of equation. So just to show that there may be different type of components. The solar panels, also another type of equation where depending on the radiation and other meteorological factors. Also, what we're not considering here is the reliability, but we have plans to consider the reliability, especially on wind farms, because we know that when we have a certain evaluation, when they implement it, actually it's always more costly than what it actually appears on the calculation because of the repairs and everything that has to be done. So we have to include here the reliability factors that we are not including right now. So the approach, what we take is a genetic algorithm. The GA, well, it's a meta-heuristic approach. It cannot be applied to this problem directly because we don't have actually strict function. We have some parts of the function that can be actually evaluated with formula and everything, but we have other parts that cannot be evaluated with formulas, but we have to run a simulation. So what we do is that we introduce simulation techniques in the evaluation function, where at the end of the evaluation we have the values that go into the formulas, and then that way we can evaluate the different objective functions that we have. So this is the approach that we have. Just to let you know, so for every combination, as I showed you before, we have many combinations. Let's say that's a combination, so we call that an individual or chromosome, and that's a gene, just a nomenclature. That's a chromosome. And each chromosome represents a potential solution. It means that each chromosome can be evaluated in either an objective function. And then we have a population, where the population, of course, consists of many different individuals. Every individual can be evaluated. And then, from the selection theory, from Darwin's, the fittest members should survive, and then the weakest do not return. So what we have is the fittest members. We play the roulette game, so the probability of survival is more for the fittest individual and less for the weakest. That's how we do. And then the ranking selection, we put the fittest also on the top, and then the weakest at the bottom. And then we do the elitism, where 70% is regular population, and the top 30% automatically goes into the next generation without doing anything, because they are the elite of the previous generation. That's what we have over here. And then, how do we do the crossover? Well, the primary objective of the crossover is actually to combine different solutions as emulating sexual reproduction to have offspring. So we have parent 1 and parent 2, and then we have offspring, right? We select a crossover point, in this case over the 3 and 4, and then we just swap the genes. We also have the mutation. A small fraction of the population goes into random mutation. We select a point, random, and then we change the numbers by random. So that's how we introduce the diversity into our population. So the flowchart. This is the flowchart of a genetic algorithm that we're using. This is a traditional one. However, in the objective function, right now what we're trying to do is we introduce a simulation technique to solve for the elements that cannot be solved using a regular calculation, regular math. So what we do is basically we just do a simulation to come up with those numbers, and then we plug them into the equation. Of course, the simulations are based on the meteorological factors, distributions of the wind and the solar, like Rayleigh distribution, Weibull distribution. So depending on what distribution you are utilizing, you get different values for the objective function. And actually, what we're dealing right now is what is the impact of having different distributions or different forecasting of the environment on the system. There are some systems where it doesn't matter really which type of forecasting you're utilizing. You actually obtain the same solution, the same best solution, best combination. But there are other cases where even a slight change varies very crazy the solutions. So we are analyzing that right now. We have a case study. Well, we have different case studies, but this is the one that we are having more work. For El Paso, this is the wind speed regular for El Paso. This is also the solar radiation here for El Paso. By the way, some of the measurements over here are being confirmed by some guys there in the laboratory in engineering. They have a device to measure the radiation of the sun. We have many data, and so with this microgrid, hybrid microgrid, basically what we do is we plug in everything and then we solve it. This is what we have so far after 20 generations, but we have it in a single objective function. After 20 generations, we reach an optimal solution, and it converges to a single solution. And for the other one, after 35 to 40 generations, what we have is Pareto from starts to stabilize in a shape. So we believe that after 35 to 40 generations, Pareto from is found, usually. Over here, we divided the global warming potential into the CO2 equivalencies and the nitrogen oxides. What we have so far is that the Pareto fund that we obtained with this method is actually better than what we obtained with a previous method that is developed by the National Laboratory, the Renewable Energy Laboratory. That it's a Homer software, which is a single objective tool, but it can be also expanded to be multi-objective tool, and then by doing that we obtain this type, the bottom type of Pareto set, which is clearly much less than the one that we are obtaining right now with the genetic approach. This is what we have so far. This is the presentation. Thank you. Well, this is some future work, what we're trying to do. Do you have any questions?
Okay, thank you very much. Questions?
I have two questions related to the Pareto fund. You end up with this Pareto fund, but I believe you need to pick from that Pareto fund a solution that is best.
Oh yes, that's the post-Pareto analysis. We have different types of post-Pareto analysis approaches. We have tried, of course, the traditional, like the ideal point, but we have also the k-means, the Gesot. We have tried the Gesot. But for example, in strange Pareto sets, for example, this one at the bottom, the k-means and the Gesot doesn't work because actually what they do is they give each point as the representative of its own group. So over here at the top, we can use more traditional like k-means or Gesot, but at the bottom, what we have tried right now is game theory approaches when each dimension is its own player, and then the player is trying to optimize its own profit or utility, and then at the end they obtain an equilibrium, a Nash equilibrium of the game, and then that's how we pick when we have a small Pareto like in the bottom. But at the top, we use usually we're trying to use the Gesot, which is well, that's post-Pareto analysis. We're not covering that right here,
but I think the question was caused by probably misunderstanding, because in the beginning, when you started talking, it sounded as if you're doing the optimization.
Yes.
But then you switched to multi-objective optimization. And I think Annibal's question, because he's still under the impression that you're doing optimization. And you need to find the maximum. But actually, he said that, but he's not. He's doing multi-objective optimization. So the goal is to produce the Pareto set.
I see.
Right?
Yes, actually, the Pareto set can
no, I mean, you don't have one objective function, you have several objective functions.
Yes.
So that was not clear from the beginning.
Well, I missed that part.
Right. No, that was not said. It was not explicitly said. That's why I'm saying it's confusion, because when in the beginning you said we cannot directly apply genetic algorithm, but the only reason you said is that to compute the objective function you need to apply some algorithm. Well, okay, so you need to apply an algorithm. That's normal. But it turns out you don't have a single objective function, you have many objective functions. So what you need is really to produce the Pareto set.
Yes.
And then, of course, you have a lot of heuristics on what to do, but this is already not on the level of the original problem. This is what you do. Okay.
Yes. Basically, when we obtain the Pareto set, we understand that as the optimization.
Because it's multi-objective optimization.
Yes.
That's different from
yes.
optimization of a single objective. Yes. How is it? Is it like a pioneer work, or is somebody doing this? So, like
pioneer, like never done before?
Yes, or somebody's doing that. Or this is
no, there are different. Well, this is our work, but there are different works that have been done. For example, in Spain, they have many researchers in renewable energy in Spain also.
And so they're also solving this kind of problems.
Yes.
How is your result better? In what sense? Or it's just a new approach, or you already have some results which are better than anything that, I mean,
for example,
how do you compare with what is done before?
For example, in Spain and also in the renewable energy laboratory, what they do is they take the entire universe of solutions and then they go each one by each one. So what they do is they cover the entire universe and then they say, okay, this is the best.
Oh, so they're not using genetic algorithms,
no.
They're just using exhaustive search. Okay.
Yes, they use.
That's expensive. So it's expensive. Okay.
Yeah, very expensive. So what they do is they're constrained to small problems, and we're trying to expand it.
So this Homer tool is also you doing it, right? It's a different tool.
Yes, this is from Homer, which is a single objective tool, and then we expanded it to be double objective.
Oh, so you yourself expanded it. Okay.
Yeah, we expanded it by ourselves, and then we obtained this. And this is entirely from the genetic algorithm.
Okay. Other questions?
Just real quick, how did you settle on a genetic algorithm? How did you think that it would apply to what you were?
Basically, we were trying to do also.
Okay, can you mind? We can switch.
We were deciding between the genetic algorithm or the taboo search, but basically it appeared to be easier as a first approach. As a first approach, it appears to be better the genetic algorithm.
So what's the other alternative?
The taboo search. The reason why we were taboo search.
Taboo search, okay.
Taboo search. The reason why we are considering the taboo search is because to actually evaluate each individual takes very long time because the simulation is involved within each evaluation, and then the simulation takes long. So what we're trying to do is to avoid everything that we already know, or some type of dynamic programming maybe, or taboo search. We are not really sure right now. So this is part of what we're doing. So genetic algorithms basically because it appears to be easy and fast to implement as a multi-objective approach. It's an algorithm that we know already, so we implement it.
Okay. Thank you very much.